Welcome back to the Neurostimulation Podcast. I'm Michael Passmore, Clinical Associate Professor in the Department of Psychiatry at the University of British Columbia in Vancouver, Canada. In the Neurostimulation Podcast, we have discussions with clinicians and researchers in the field of clinical neurostimulation, neuroscience, and general health and wellness. We also explore research articles and textbook chapters. And today we're going to continue our exploration of the textbook called Practical Guide to Transcranial Direct Current Stimulation. This is a foundational reference for clinicians and researchers alike. Today we're going to talk about Chapter 5, Transcranial Direct Current Stimulation, Modulation of Neurophysiological Functional Outcomes, Neurophysiological Principles, and Rationale. This textbook chapter talks about measuring change, and it explores how tDCS shapes brain function through neurophysiology. In today's episode, we're going to take a deep dive into how transcranial direct current stimulation, or tDCS, actually changes brain function as revealed through neurophysiology and functional imaging. We're going to explore what's happening at the neuron, network, and behavioral level, and why this matters for both researchers and clinicians. First of all, why measure neurophysiological outcomes? The big question isn't just whether tDCS works, it's how. So to answer that, we need physiological measures. These allow us to quantify how stimulation affects brain function, improve stimulation targeting and parameters, and understand how brain plasticity is shaped and how can it be modulated non-invasively. From evoked potentials to functional MRI, modern neuroscience gives us the tools to peek under the hood and see what's changing in real time. So what are the tools of the trade? Let's run through the main methods used to measure tDCS-induced neurophysiological changes. The first is TMS evoked motor potentials, or MEPs, especially over the motor cortex. The second is EEG and event-related potentials, or ERPS, for high temporal resolution. The third is fMRI, functional MRI imaging, and PET, positron emission tomography imaging, to capture network and metabolic changes. The next is combined TMS EEG to map cortical excitability and connectivity in the brain in real time. And finally, pharmacological interaction studies to dissect neurotransmitter-specific effects. Each of these techniques has its own strengths. For example, EEG for timing, fMRI for spatial detail, and TMS for direct probing of excitability. So what happens under the electrodes in tDCS? Let's talk about regional effects. When you apply tDCS, you're modulating membrane polarization of the neurons directly under the electrodes. For example, the anodal tDCS usually increases neuronal excitability, and the cathodal tDCS often reduces it, although this varies by brain region and context. These effects have been most studied in the primary motor cortex, where changes in motor evoked potentials provide a relatively straightforward measure of cortical plasticity. But it's not just about what happens locally. Let's look at remote and network level effects. Brain is a network, not just a collection of isolated parts. So tDCS affects not just the region under the electrodes, also functionally connected areas through changes in signal propagation and resting state connectivity, including between frontal cortex and subcortical hubs like the ventral tegmental area, or VTA. tDCS can also strengthen or weaken communication within large-scale brain networks, and that has powerful implications for conditions like stroke recovery, chronic psychotic conditions like schizophrenia, and neurocognitive disorders like Alzheimer's disease. So what's the role of state dependency? tDCS is not acting like a magic button that can turn parts of the brain on or off. Instead, it appears to be interacting with what the brain is already doing. So if you stimulate using tDCS during a task, for example, motor training, training a particular kind of movement, memory encoding, so learning a new task or learning a new fact, or emotional regulation, the effects can be enhanced or changed by the tDCS. This kind of an effect is called state-dependent neuromodulation. Here are some examples. When tDCS is paired with something like cognitive behavioral therapy, it may increase the treatment effects in people suffering from depression. Or when tDCS during rehabilitation exercises in physical therapy settings, when a person is recovering from a stroke, may potentially improve that person's outcomes during their post-stroke rehabilitation course. This insight appears to be shaping task-concurrent stimulation paradigms that integrates tDCS with other kinds of activities, such as behavior or other learning paradigms. So how about modeling and the quest for personalized treatment? Computational modeling appears to play a very important role in modern tDCS research. This helps to predict current flow through different head anatomies. It is guiding electrode placement and dosage parameters for individual patients, and it's informing our understanding of multi-region stimulation effects. These kinds of models are among the most advanced in neurostimulation, and they're now helping us to link stimulation to behavior in more precise ways. Overall, this is a step towards personalized and what are called closed-loop tDCS protocols. So let's talk now about this connecting brain changes to behavior and therapeutic outcomes. Ultimately, what matters most is functional outcomes. So can tDCS-induced brain changes improve memory, reduce depression, or enhance recovery after brain injury? There's increasing evidence that it can, but the relationship between the neurophysiology and the behavioral outcomes are complex. For example, functional connectivity changes often correlate with improvements, but EEG or MEP changes alone don't always predict outcomes reliably. This particular issue is a major area for future research, identifying biomarkers that bridge the gap between physiological modulation and real-world improvement. What are some of the challenges and clinical implications? Research is making progress at lightning speed, but many questions remain. For example, why do some people respond to tDCS whereas others don't? How do genetics, medications, or even things like the time of day seem to affect outcomes from time to time? What protocols work best for which symptoms in which individuals? Clinically, this means that we need better predictive models, more tailored protocols, and ongoing research into mechanisms of action. Yet the promise remains strong, especially for conditions marked by network dysfunction or impaired neuroplasticity. So in closing, tDCS isn't just a tool for altering mood or memory. It appears to be a window into the brain's plasticity. Through these kinds of neurophysiological measures, it appears as though we're increasingly able to track change, optimize treatment protocols, and move towards individualized, personalized care. In this chapter, we've explored how tDCS is both a scientific instrument and a clinical intervention. And the more we learn about how it shapes neural function, the better that we're going to be able to harness its power to improve patient lives and wellness. Thanks again for tuning in. If you found this episode valuable, please share it with someone that you think might also be interested. And don't forget to like and subscribe. Please leave questions or comments in the comment section below and suggest content that you might be interested in hearing about in a future episode. In the meantime, be well, stay curious, and I'll see you next time on the Neurostimulation Podcast.